Hi everyone, welcome to this episode of Keipert Labs. Today we're going to be talking about buffers. So we're going to start off by asking ourselves, what is a buffer? So thinking about, okay, how would we define that? I'm going to go through a particular example, so using these coloured buttons that you've seen before to actually illustrate kind of how this works. We're going to talk about how buffers can work to minimise pH change in a system. And then we're going to go through just a quick natural example about where we can find a buffer. All right, let's get into it nice and quickly. Okay, so we first thinking about, okay, so for a buffer, we've got a mixture of a weak acid and its conjugate base. So its conjugate base in high concentrations. Okay, so around about 1:1 ratio. So that is about 50% of each. Okay, so a buffer. So a buffer is this combination in solution, this mixture of a weak acid and its conjugate base. So maybe we might be thinking about, say, acetic acid and the acetate ion together in solution. Maybe we're thinking about carbonic acid and the bicarbonate ion. Maybe we're thinking about dihydrogen phosphate and the hydrogen phosphate ion. Okay, that these are, or maybe we're thinking ammonium and ammonia. So a weak acid and its conjugate base together in solution in roughly 50-50 proportions. Okay, now the fact that there's about 50-50 proportion is quite important here. Okay, so with this in mind and seeing some common examples there, I'm going to use these color buttons and kind of walk you through a more generic kind of example of kind of how this works. Okay, so let's think more generally that we've got a buffer that's made of this generic weak acid. Pardon me while I change my markers, see if that can improve. This generic weak acid HA, but then when we put it in water, we get formation of A- and then hydronium. Okay, so if I use these colored buttons underneath to kind of help represent things, so maybe, okay, let's say that the blue represents our proton and A represents our H-, our A-, and then a yellow represents a water molecule. So over on this side we've got a red one by itself, and we've got our water molecule with its extra proton attached over here. Okay, and so what we're talking about over here is let's say let's talk about 4 of these. Okay, and okay, so we've got pardon me while I just get the board set. Okay, so we've got, now we would have stacks more water molecules than this, but just for consistency's sake, okay, and to show you a balanced kind of sort of setup here. Okay, so this is what we might see with a buffer. Okay, so the main things that you need to be noticing is that we would have roughly equal proportions of HA, the red-blue combination, and then the A- over here, its conjugate base. So this is the acid and its conjugate base in roughly equal proportions. Okay, now the reason that matters is in terms of how a buffer works, thinking about it in terms of pH change. Okay, so let's say all of a sudden, because of something else, yeah, actually what I might do, pardon me for changing this up on you a little bit, I've got to give myself a few more buttons. Okay, so let's say I started off with 3 of each. Okay, and let's say I've added in some extra acid into this system. So that is, I've added more of that H3O plus over here. What happens is that a buffer can work to minimize the pH change because this equilibrium can shift. What it does is it shifts to try and remove the added H3O plus, and so it will move to the left. Okay, so what it does, so we need to try and take this out so we can get it to combine with that. Okay, and so then we can combine again. And so we've removed the change in pH. Okay, and in doing it by shifting the equilibrium, in this case shifting it to the left, okay, to replace it, or to kind of remove this, and so then we've made more HA. Okay, now let's kind of reset things. Okay, so let's Okay, so let's say, now let's take our original system back. Okay, now let's say that we've added hydroxide. Okay, so now remember that hydroxide will react with hydronium ions that are present to form water. We'll get a neutralization reaction going on. So let's say, because of that, that 2 of our hydronium ions are taken out, okay, by this reaction. They've kind of removed out of the system. What's going to happen is that we're going to, in this case, we're going to shift to the right to try and replace them. And so in doing so, what we would do, okay, that our HA would react, okay, bumping this up, react with some more water to replace our added our hydronium that we had lost, and in doing so we're forming more A-. Now we've reduced our amount of HA. Now there would still be very large proportions of both left. We would have more A- now, we've tipped the balance slightly, but in doing so we've regained our original amount of hydronium. So what has happened is that now that the pH is pretty much as it was, our hydronium concentration is not really changed, okay, and in the way that it did that, it was by this equilibrium between the acid and its conjugate base. We could move one way or the other depending on which whether hydronium was added or removed. Okay, now you can see even just with this simple illustration that there has limitations. So let's say that this was the amount all that I'd had, and let's say that I had removed all the hydronium, and so then this needed to react, and we ended up with this. Now you can very easily see we now have no HA left. There's no further ability for this equilibrium to shift to the right because we've used all of this up. So if all of a sudden this hydronium was taken out now, then this buffer cannot absorb that change in pH. We'd say that the buffer's been exhausted, or its capacity has been removed. Okay, and so then any extra hydronium that we either take out or that we add would now change the pH of the solution like it would if it was just water. Okay, so that's just showing that a buffer doesn't have an unlimited ability to absorb changes in pH. If we use up one of those reactants, then there's nothing more that we can do. Okay, but as long as we still have both HA and A- in solution, we still have the ability to absorb changes in pH. Okay, so we've talked so far about defining what a buffer is. We've used an example. We've talked about buffers and pH change. Okay, and so now just to kind of wrap things up, let's have a little look at a natural example. Okay, so the example that we're going to look at is one that occurs in our bloodstream to help keep us alive, so which is always nice. Okay, so we've got, it's called the carbonic acid buffer. Okay, so we get carbonic acid and water in equilibrium with the bicarbonate ion and hydronium. Okay, so we have this buffer situation over here, okay, between these two things, between the acid and its conjugate base. Now the reason that it's also particularly interesting in a biological setting is that, remember that carbonic acid can break down to form, or can be involved with carbon dioxide and water. So which you can imagine is very useful in our system because we breathe in, we breathe out carbon dioxide all the time. So we have the ability to help not only control pH, but then we also have an extra external mechanism to keep things in check, kind of like a redundancy, if you like. That the system has kind of a backup or a way to keep it in check. So what happens, I'll just take that out for the moment. Okay, so just like we could see there before, that so that if we've got kind of particles of H2CO3, HCO3-, so then if the system if it becomes too alkaline or too basic, That is, if levels of hydronium have dropped, then it's going to shift to the right to replace it. And in doing so, carbonic acid goes down, our bicarbonate goes up to help replace it. Okay? Likewise, if we add extra hydronium ions into our system, if your blood starts to become too acidic, then we can shift to the left to try and remove it, and we use up some of our bicarbonate and we form more carbonic acid. If we form too much carbonic acid, or what that can do, the reason that this kind of kicks in is that then that can change to form carbon dioxide that then we exhale, and so then reducing levels of this back down in a different way. Okay, so this helps to keep our blood to a very narrow pH range of 7.35 to 7.45, a very specific level, because if it's too acidic, if it's below 7.35, we have what's called acidosis, and if it's above 7.45, we have what's called alkalosis. So having this buffer alongside other buffers inside your blood help to maintain a very specific pH range, absorbing extra changes in acid or base. Okay, that wraps it up. Thanks very much for watching. Bye for now.